Okay, today let's discuss boundary layers. So the boundary layer is really a high Reynolds number concept. So remember that the Reynolds number is defined as the density times some velocity scale times some length scale divided by the viscosity, and it represents a ratio of inertia to viscosity. So the boundary layer is going to be a concept which is really valid at high Reynolds number. So let's start with an easy case and then we'll work up to the problem we're really interested in. So let's imagine that we have a flat plate. And let's imagine this plate is very long. And on top of the plate we have a fluid. Time equals to 0, everything is at rest. As soon as time equals to 0 or greater than 0, we pull on the plate and we pull it with a constant velocity. I'll call it u0. And now we want to understand what happens in this case. So we could resort to our Navier-Stokes equations, conservation of mass and momentum, and I'll just write this out in 2 dimensions. So there's conservation of mass and momentum in the x and y direction. Now this is the same that we did in a bunch of our previous problems, but we'll just repeat the exercise. So we're going to assume that everything is long, and therefore there's no real difference at any particular fixed location because this goes off to infinity, even though I haven't drawn it as such, and this goes off to infinity. So we're just going to kill everything that has a derivative with respect to x equaling to 0. So in conservation of mass, we lose that term. Conservation of momentum, we lose those 2 terms. In our viscous term, we lose those 2 second derivatives with respect to x. And let's think about the pressure for a little bit, because we know that sometimes you have to be a little bit careful just eliminating the pressure. But here I'm driving the flow by sliding the plate, so I'm not imposing any pressure from one side or the other. So we expect that derivative to be equal to 0. Now, conservation of mass tells us that there's no change in velocity with respect to y, but we know at the plate v is equal to 0. And since v can't have any derivative, it's equal to 0 here, it must equal to 0 everywhere throughout the fluid. So this assumption in conservation of mass implies the vertical velocity is 0. So I can kill all of those terms, which kills the entire y momentum equation and leaves our balance here being the time derivative of u is equal to the viscosity over the density. And we've seen that we have we provide this term a different name called, in a different symbol, nu, the kinematic viscosity. And so what we're left with is our governing equation looking exactly like what we found when we did heat conduction. So what do we expect at time equals to 0? Our velocity profile will be 0 everywhere. As soon as we pull on the plate, we kind of expect a profile that looks like that. And as time goes by, this thing will thicken and thicken and thicken as momentum diffuses from the plate where we're driving the flow out into the free stream. And this thickness will grow with time. So we have our equation. And let's see if we can guess from just sort of scaling arguments what the thickness of this layer is, where we have a transition of velocity from basically being at rest to the velocity of the wall. So we'll do this by scaling our equation. So I'll define a new velocity being the actual velocity divided by the velocity of the plate, which we're calling u0. We'll divide the time by some arbitrary scale t0 that I'm not going to define yet because it's not clear what that time ought to be. And I'll define my coordinate y to be scaled by some dimension delta, which is going to be kind of like our thickness of our layer. So if we carry this out just by substituting these variables in up here, we've done this before. So we substitute those in, then we can pull everything that's a constant out of the derivative. What we'll find is the u0 cancels, and then I'll just group everything to one side, so what we'd have left And so what we find by doing this is that we have kind of one parameter that pops out, which is that sucker right there, and that has the right units because the kinematic viscosity has units of length squared over time. So when I multiply by T naught, I have units of length squared. Delta has units of length squared. So this just sort of tells me, at least qualitatively and sort of scaling wise, that the thickness of this layer is going to grow as the square root of the kinematic viscosity times the time. And this is just like what we found in heat conduction, so this result shouldn't be terribly surprising, but in heat conduction this is replaced by the thermal diffusivity. Here we have the diffusivity of momentum. Now let's talk about another problem we might be interested in, which is where we're going to have a free stream velocity which is uniform and has a magnitude u naught, is going in the x direction, and it's going to approach a thin flat plate, which essentially extends off forever. And so what we'd observe if we did this experiment is that as the velocity, if we measured the velocity at some distance down the plate, we'd get a profile that looked like this. So it would be 0 at the plate, and it would rapidly go up and then basically be equal to the free stream velocity so far away. So there'd be some location where we could say more or less, for all intents and purposes, the velocity has returned to the free stream value. And if we did this at several locations on the plate, what we'd find is that the thickness of this layer sort of grows as we move down the plate. So it would look, at least qualitatively, something like that. And at every location, we could describe the thickness of this layer to be delta. Now we saw in the previous problem where we impulsively started the plate that the thickness delta squared grew something like the kinematic viscosity times time. Here what we can do is we can prescribe time, it's that being the time that it takes for a fluid particle to travel from the front to the point where we're interested in, right? Because delta changes with x. So our coordinate direction x will look something like this. So that means in this problem then that we replace time simply by the distance we've traveled, x, divided by u naught. We could rearrange this expression and put it in dimensionless terms, so delta over x. Actually, let's do it as delta squared over x squared, being something like nu over x u naught. Now we see that this is a dimensionless number, which is really the Reynolds number, where it's based on x. So our length scale in our Reynolds number is x. The coordinate direction, or the distance from the leading edge from this point to the point where we're interested in knowing what delta is. So we could also write this then as delta over x being something like the square root of 1 over the Reynolds number, where the Reynolds number is based on x. So this doesn't tell us the exact answer, it just tells us that we might expect some sort of behavior like this. And this also tells us that we expect then that the thickness of this boundary layer, if we look at this expression here, to grow as a square root function. So it'll grow as the square root of x. Now it's important to realize that in the boundary layer there is vertical flow. We can see that by drawing a control volume. So if I draw a control volume that looks like this, and we simply look at conservation of mass, we see that on this boundary, I'll call it 1, we have a flow rate in u naught times the height, delta. On this boundary, we have a flow rate out, which is our function u of y, and I'll say is the integral dy. And so since those can't be equal, this area here must be balanced by flow, which is coming out of this boundary. And I'll write that as the integral of the vertical velocity dx, and those have to sum to 0. So we can kind of see from this argument here that we have something that's like u naught times delta. Here we have something that's like v times x. And so that tells us then that we might expect the vertical velocity we might expect the vertical velocity to be on the order of u naught times delta over x. So if delta over x is a small number, then we expect that the vertical velocity to be small. What this means is that if we write out the Navier-Stokes equation, so let's write out the x momentum at steady state with no applied pressure gradient, we would have this for the x direction. And what that means is that in the boundary layer, we can't ignore the nonlinear term, or the right-hand side of the equation, right? Because if we think about it, this is kind of a small number. It scales as delta over x, but the gradients in y are the big ones. So this is a big number, right? Because u changes dramatically in this direction because it's changing, right, from the 0 to the free stream value over a distance delta. So this is a relatively big number. On the other hand, this term is relatively large. The free stream velocity is high, but the changes in x are kind of less dramatic. So this is big, and this is small. So really, we can't very easily anyway argue that this term should be neglected, so we have to retain it. And that makes the analysis of the boundary layer problem a little bit more complicated. However, we have Blasius, who was a student of a very famous aerodynamicist, essentially the founder of modern aerodynamics, a guy named Prandtl, Ludwig Prandtl. So we have Blasius, who was Prandtl's student, to thank for essentially solving this problem. And so I won't go through the analysis because it's a little bit complicated for our purposes, but what he found was the velocity profile divided by the free stream velocity, u naught, turns out to be written as a function of y divided by the square root of the kinematic viscosity times x over u naught. And the form of this solution is what we would call a similarity solution, because we're mixing the coordinate direction y and the other coordinate direction x in a single variable and writing our normalized velocity profile as a function of that. If you're interested, you can look up this result if you just look for Blasius solution. However, I'll just give you the key results. So the key results are the thickness of the boundary layer is 5 divided by the square root of the Reynolds number. So just by scaling arguments, we decided that it ought to scale as 1 over the root Reynolds number. So the Blasius solution justifies that and gives us the coefficient out front, which is 5. It also defines the coefficient of friction, which could be defined as the local shear stress, which is a function of x, divided by the kinetic energy of this factor 0.664 divided by the square root of the Reynolds number. Now this factor 0.664 just comes from the analysis. It's actually calculated numerically because you end up with something that you can't integrate necessarily by hand, but it's just a number that comes out of the analysis. And likewise from this, we could define the coefficient of drag, which we would define as the total force on the plate per unit width divided by, and that would be 1.328 divided by the square root of the Reynolds number. So the Blasius solution tells us the thickness of the boundary layer and also the drag on the plate. And all of these things scale as 1 over the Reynolds number, which is based on x. So again, we have that definition. So this Blasius solution is really only good when the Reynolds number based on x is less than 10 to the 5th, or sometimes you'll see in books 10 to the 6th. I like to use 10 to the 5th because that's a sort of more conservative estimate. But the exact number where the solution breaks down is highly dependent upon the exact conditions of the experiment. Do you have a lot of free stream disturbances, or is the velocity profile coming at the plate really truly smooth? Is the plate truly smooth, or is there roughness? So we'll just stick with the 10 to the 5th number, but it's important to realize these transition numbers where solutions break down are often not very precise. But what we'd observe then in practice would be the following. So here's our plate. And here's the location where the Reynolds number becomes equal to about 10 to the 5th. So from the leading edge up to this point, we might suspect then that the Blasius solution is quite good, and in fact that's what we observe. Now let's go further along, and let's say we're out here where the Reynolds number is something like 10 to the 6th or higher. What we'd observe out here is the boundary layer is much thicker than it was, and now it's turbulent, so there's lots of fluctuations, there's lots of eddies and swirls and sort of complex structure going on here. Now if I took a little probe and we put a velocity probe at a single point and we plotted the velocity at that point as a function of time, we could describe a mean value but we'd see lots and lots of fluctuation around that value. So it'd be kind of going up and down, up and down, up and down. It would never be steady. And if we measured an average velocity profile, what we might see is something that looks at least qualitatively like this. So here's the free stream value. We'd see maybe a slight departure from that, but not a whole lot of change over a great distance. And then a very, very rapid change right at the bottom. So our average velocity profile might look something much blunter than it did in the Blasius solution, and much more dramatic transition right at the wall. And the reason it's so thin at the wall is because now we have this swirling motion, lots of eddies, which can carry high momentum fluid from the upper reaches of the boundary layer down to the plate. So it kind of blunts this thing out quite a bit. Though the region where we have a departure from the free stream velocity might be quite a bit thicker, much of that change happens over a very, very, very narrow region. Now, what happens between this point and this point, where we go from the Blasius solution to kind of a fully turbulent one, is also a little bit complicated. And again, a lot of this depends upon the details of what you observe. But in general, there's some sort of, this layer kind of grows maybe a little bit randomly. But what's observed is that first some waves start to develop. So you see some sort of wavy pattern in here. If we looked at the plate from the top, so this would be sort of a top view, looking down on the plate around this region. If we injected smoke in our flow, we might see some wavy stuff going on here. These waves are called Tolmien. I'll probably spell this wrong. Schlichting waves, named after the people who discovered them. But we see some wavy structure here. And then these waves tend to become wavy in this direction. And then they'll sort of pinch off and become these kind of triangle-y looking structures. And then what's observed are some sort of turbulent spots. Some sort of random spots of turbulence. And then it just becomes totally turbulent after that. So this is kind of a basic picture. It's very complex, and the exact sort of transition here depends very sensitively on the roughness of the plate and the sort of quietness of the free stream velocity. But if you set things up very carefully in the lab, this is kind of the basic picture that you observe. So it's kind of a little bit complicated, but we have kind of the Blasius solution being good for some of the region and it being sort of wholly turbulent for the rest of the region. And we just have to remember, keep in mind, that the transition between those is not a precise thing. Describing the turbulent region is actually quite complex, but we can do it empirically because we can show by dimensional analysis quite readily that things like the thickness of this boundary layer divided by x has to be a function of the Reynolds number, and things like the coefficient of friction, which we defined as the local shear stress divided by 1/2 rho u naught squared, also has to be a function of the Reynolds number. So we know that they're functions, we just don't know what those functions are. So it turns out we can measure them. So this is purely empirical, so the functional form and the factors here, there's no magic behind them, it's just what we measure. But for turbulent, kind of common correlation would be that delta over x is equal to 0.37 over the Reynolds number based on x to the 1/5 power. And another empirical correlation would be the coefficient of friction is 0.592 divided by the Reynolds number based on x to the 1/5 power. So these are just empirical fits to data. So what we might observe then is here's our plate. The thickness of the boundary layer delta of the leading edge grows as the square root of x. At some point we'll say here's the Reynolds number based on x equaling 10 to the 5th. And if we plot our empirical correlation for the thickness of the turbulent layer, it might look something like this. If we look at the scaling, we'd find that this grows as x to the 4/5 power, so a little bit steeper like that. And at a Reynolds number of 10 to the 5th, they wouldn't quite line up. And so what that means in reality is that something, you might follow this solution for a while, then it's going to break down, and maybe something that's not so repeatable happens, right? So if we did a different experiment with a different plate with a different roughness, we might find it looks something more like that. But at high Reynolds number or far distances down the plate, we would match this turbulent correlation. Up near the leading edge, we'd match the Blasius solution. There'd be some sort of random transition in between that would kind of depend really on the details of what's going on. So we sort of hop between these two solutions with this sudden burst in thickness of the boundary layer. If we looked at the coefficient of friction, which we define as the local shear stress divided by 1/2 rho u squared, and we plot that as a function of the Reynolds number based on x or distance down the plate, what we would find then, and we did this, let's imagine this is in log scale, so this is the log of the Reynolds number and the log of that. We would define this being a 1/2 power, this being a 1/5 power, that being the laminar Blasius solution, this being the turbulent empirical correlation, and in any given experiment, some sort of trajectory that hops from one solution to the other. It's also important to realize that while I'm drawing this structure out here, the thickness of a boundary layer is a line. In reality, it's not necessarily a line. It's a line when you average over time, but at any given instant, it might look quite different. Here's a few images from a book called Album of Fluid Motion. There's a picture of a turbulent boundary layer. We can see that at this particular instant, the structure is quite irregular. However, if we averaged over time, we'd have kind of a smooth layer where there was disturbed flow and a layer where there was turbulent flow. And just down here is a slightly different one. What we see lots of sort of structure going on here and lots of irregularity. However, if we average things over time, we get the structure and the correlations as I described just a second ago.